Okay, so today is actually going to be our last lecture of the unit. I'm getting rid of the complex ion stuff for tomorrow, and I'm going to reinsert that into a future unit where it fits a little bit better. So what we're going to focus on today, it's actually going to be kind of cool because it's giving you a shortcut to reactions. When up to this point, we ask you to write the net ionic equation, you probably think, oh, that takes forever because I have to write the whole thing, and then I have to balance it, then I have to split stuff up, and then I have to cross stuff out. Well, that's well and good when you're asked to do that specifically, but if they just ask you to write a net ionic for something, it would be nice to have a quicker way to do it, and that's what I'm going to show you. You're not going to be specifically tested on this method, but it's a method that's going to be good to have in your back pocket to use throughout the whole year anytime you're asked for a net ionic equation. Okay? So we're only going to focus on redox equations, and you're going to see a lot of equations or redox that you might not ever have considered as being redox before. So some of the tricks of the trade of doing this quick method is to, number one, never write down any group 1 metal ions or nitrates. Unless they say it's included in a solid, why would I not do that? They're always soluble, but what are those things called that we cross out? Spectators. They're always spectators, so why write them down in the first place? So that's going to save us a lot of time. If you approach these problems as thinking about a charge going up and down, you can predict what's going to happen without really even thinking about, oh, it's a single replacement, and this is going to do this. You can just look at the charges and know immediately what your products are going to be. This go to metals first thing is a demo rule, and I will explain it to you when we get to an example that uses it, okay? And then the last rule is make sure your charge and atoms are balanced. You're really good at balancing atoms, but now we got to pay attention to the charge. The charge overall has to be the same on both sides of the equation, okay? So best way to do this is just to jump in and start working problems, and you're really going to be surprised how much faster you can do net ionics now. A piece of aluminum metal. What are we going to write down? Aluminum. We don't have to worry about states. This is just us getting quick reactions, okay? Is added to a solution of silver nitrate. The fact that it says solution means it's an ion. So anytime you see the word solution, it's going to coincide with the solubility rules. So you know that all nitrates are soluble, so it makes a solution. You're going to write this stuff down in ions immediately. You're not going to write it together, write AQ, and then eventually break it up. You're just going to break it up into ions right away. But what are we only going to write down? The silver. Why aren't we going to write down the nitrate? Because it's a spectator. So now, this is a part that's really cool. Single replacement reactions are redox reactions. Okay? So all we need to do is make something go up in charge and make something go down in charge. Let's do that, and then I'll correlate it back to the net ionic. Aluminum can only go one direction. Which way can it go? Up to what? Al plus 3, right? Silver then has to go down, and what's it going to go down to? Only one option. Ag, what? Solid, right? Can it do anything else? Silver can either be plus 1 or 0. That's it. Aluminum can either be plus 3 or 0. So aluminum went up in charge, silver went down in charge. Now we're done except for the balancing portion. Our atoms are balanced, but our charge isn't. So what should I do? 2? No. What's our overall charge on? We can add electrons, but that's not going to make the balancing happen. That's for half reactions. Just do by inspection here. If we put a 3 here, do you see how that gives us 3 pluses? But what did that do to our number of silvers? Put a 3 here. So this is the fast way to do it. So how does this even resemble the net ionic? This is the net ionic. Really quick. Aluminum plus silver nitrate. In the past, you'd predict, so you'd write AlNO3 plus silver, right? And then you'd go and you'd split them up, right? And so you'd split them up, and then you'd end up canceling out this guy, and then you would have balanced before you split up. So do you see how you would have gotten the same thing? So this is the short way of doing it. Isn't that a little bit shorter? I like it. I think it's good. So we're going to do a lot of problems like that, but first I want to introduce you to this. This problem is a metal plus water. This, from here on out, is going to be known as a push-up problem. If you don't believe me, you can ask organic students. If you miss a problem of a metal plus water from here on out, you will do push-ups. It's an important reaction, and looking at it and knowing it's single replacement, we can't bust that up because it's a liquid. My question is, what do you think the big student mistake is in this one? No, that's the answer, Grant. So what's the wrong answer? Na2O. They think you boot out the H and you make Na2O and H2. You don't, because we're looking at water the way it ionizes as an H plus and OH minus. So when the single replacement happens, we're actually making a base and hydrogen gas. So anytime you add an active metal to water, you get a base, meaning a hydroxide of some sort, and hydrogen gas. You have to know that. I don't like you having to memorize things, so this is something that you talk about throwing those metals in water and how they explode and all those things happen. This is what's going on. So what are our two products then? Hydrogen gas. I'm not going to write NaOH as it is because I'm trying to make this as a shortcut. Is NaOH soluble in solution? Yes. So isn't that group 1 metal ion thing? So I'm not going to cancel it out, but I am going to write it down, but I'm going to write it down split up. Why can't I have canceled it out? Yeah, because Na plus is not the same as Na0. So rather than just writing NaOH, because it's soluble, I write Na plus plus OH minus, which is how we would have seen it in the net ionic had we done it the long way. Now let's go ahead and balance this. I'm going to need 2 waters here, right? Because I got 2 H's and 1 OH, 2 H's, 1 OH, so I'm going to need 2 waters. But what does that make me do to my hydroxides? I need 2 hydroxides. Now all my elements are balanced, but what happened? Why did you say I need 2 NAs? Right, but okay. He's looking at it one way, but I'm looking at it with those pluses and minuses. The charge doesn't balance, right? What Grant was saying was right. He was like, well, there's 2 OHs, so you have to have 2 NAs. That's correct, but the reason is because that's 2 minuses, so you got to have 2 pluses in order to get a 0 charge on both sides. So what did that do to my sodium on this side? I need a 2. Let's try a different type of redox. Chlorine gas, so I write Cl2, is bubbled into a solution of sodium bromide. What's the only thing I write? Br minus. I don't write down Na plus because it's soluble. It's going to be something that cancels on both sides. This one's different because I'm starting out with solid. I'm not starting with the spectator. If you start with the spectator, it's always going to be a spectator. Here, that sodium is starting as a spectator. I'm sure you're like, what the hell do? I don't even recognize this as a single replacement. I'll show you how it's a single replacement in a second, but doing the shortcut, since this is redox, just look at charges. There's only one thing both of those things can do. Cl minus and Br2, which happens to be 0. All right, so now this is easy to balance because we need 2 of these. This is so easy compared to writing out the full net ionic. How did that full net ionic work? You would have written this plus this, and then you would have seen the single replacement here. So you would have made sodium chloride and bromine gas, Br2. Bromine liquid, excuse me, Br2. Sodium chloride, well, sodium is the spectator, so you would have just had the chloride ions. Isn't that what we have? Okay? So again, this is just a shortcut for doing these problems. So let's take a look at this next one. This is going to be an example of the go to metals first rule that I had, when to use it. Magnesium turnings. If y'all ever seen, like either on a commercial or in person, you take a big block of cheese and you have that little slicer and it makes these pieces that look like curls? That's a turning, okay, so you know. Magnesium turnings are added, they're solid, so it's a 0 oxidation state. A solution of iron 3 chloride, that's not a group 1 metal, and it's not anything that's always going to be soluble, so we're going to write both ions down. So we get Fe plus 3. Do you see why I split them into ions, though? Why? Because it's soluble, and what else? It says the word solution in the actual problem, okay? All right, so we're looking for redox changes with charge going up and down. This is where my rule, go to metals first, is where you need to start. If you can make the redox occur between the two metals, bam, you're done. Looking at the magnesium and the iron, can you make one go up and one go down? Yes. What can you make magnesium go to? +2. What can you make iron? I know iron is 2 and 0. I'll talk about common oxidation states in a minute, but always take your metals down to the solid state. Iron 0 is way more common than iron +2, so we're going to drop it all the way to the 0 state. Did chloride need to be there for this? Okay, I knew not to write it down at the beginning. You might not know that. Write it down and see if you need it. Huh? Because I needed to know if redox would happen between these two. I wasn't sure if it was going to happen between these two or between those two first. Okay, sometimes going to metals first doesn't work. You can't make redox happen, so you have to use the other thing. But for the most part, you know, you also want to make sure that this is not going to form a precipitate with something else. Because let's say I would have had a silver plus in this solution. I would have ended up making silver chloride, which is not a precipitate. So just write it down, see if you need it, and if you don't, move on. Now, I can balance this with half reactions a long way. I can take magnesium and magnesium +2, bring it down, add 2 electrons. Then I can bring those down, add 3 electrons. There's a quick way to do it if you want to. If you want to do the other way, you can. But what I like to see is, okay, I have a change of 2 electrons here and a change of 3 electrons here. So what's a common factor between 2 and 3? 6. So knowing I need a 6, if I put a 2 in front of here, that's a 6. That makes me need 2 irons. If I put a 3 in front of here, that's a 6. That means 3 magnesiums. This is exactly the same thing as doing the balancing that we did yesterday. Was it day before yesterday, where we took the half reactions, balanced, and then added electrons to each side. It was just doing it quickly. Sometimes you can do it by inspection like this. Sometimes they're a little too convoluted to do. All right? All right, so this is single replacement. Another type of redox that you might not have recognized was redox is all addition reactions are redox. Addition reactions can be super simple. If you have 2 elements, just slam them together. Calcium metal is heated strongly. I like how it says strongly, in nitrogen gas. If I just smack those 2 together, what would I make? Ca 3N2. So to balance this, I need a 3Ca. Now, how is that a redox? Well, calcium went from 0 to +2. Nitrogen went from 0 to -3. Addition is another redox. What does it mean to place something in a flame? Add oxygen. Yes, things do combust when you place them in flames. We're adding oxygen. So we're going to smack those 2 together. Oxygen just smacks into things when you add them, and what do we get? MgO. So I need 2 O's, and I need 2 Mg's. Another type of redox. Magnesium went up from 0 to +2. Oxygen went down from 0 to -2. Now here's some special ones. Magnesium oxide is added to a container of carbon dioxide. And I'm hoping you're thinking, what the hell? because I want you to be thinking that right now. There's a couple rules that are going to be super duper duper helpful. And I want you to take this and put it in your head. Oxides are weird. If you see an oxide from here on out as reactants, I want you to go, oh, there's something going on I have to do. So with oxides being weird, if you know the following: no acid, mo base. These oxides are known as either acid, acidic, or basic. Oh, please don't freak out, smartboard. There, it's in freak out mode again, and I'm supposed to finish this recording now without it. Fabulous. Acid or basic, there it goes, anhydrides. What does it mean to be an anhydride? Without water. So, non-metal oxides are really fake acids. Meaning, if you were to take a non-metal oxide and put it in some water, you make an acid. A metal oxide, a metal plus oxygen, is a fake base. If you were to take it and put it in water, it would become a real base. So these guys are missing water. That's all. If they had water, they'd be real acids and bases. They're kind of acids and bases wannabes. So, metal oxide, magnesium oxide, would be a fake what? Fake base. Carbon dioxide would be a fake non-metal oxide, so a fake acid. Going back to what you know, if you add an acid and a base, you always make a what and a what? Water and a salt. Since there's no water here, if we had a fake acid and a fake base, what are we just going to make? A salt. No water. There's no water. No water. So we're just going to make a salt. Tell me the name of a salt that has Mg in it, C in it, and O in it that you already know the formula of. Magnesium carbonate. It's always something that you know, and it's nothing special. And that ends up happens to balance perfectly. So recognize your metallic or nonmetal oxides as anhydrous acids and bases. And then it becomes an easy problem. So let's try this next one on the sheet. Whoa. Solid calcium oxide. What's the formula for that? CaO is heated in the presence. Now, just heated with. Take out in the presence because that insinuates it's catalyst. Heated with sulfur trioxide. What is that? SO3. So if you have this mixed in and you're like, what do I do? Oxides are weird. This is a fake base. This is a fake acid. Once you recognize your fake acid and base, you know you have an acid-base neutralization without the water, so we're just going to make a salt. Big old guess what this salt is. Calcium sulfate. It seems easy now, but again, when it's mixed up and you're like, is it addition? Is it single replacement? What do I do? Do I just get oxygen gas kicked off? If you recognize the oxide thing, you'll be able to figure it out. You wouldn't be able to balance it, so let's do it. If you cannot balance your equation, it's wrong. You've done something wrong. So do you see how that's totally not balanceable? Because anytime we change one of those, we change the other, and you'd go back and forth and back and forth. So you can attempt to make it a sulfite, but that's your internal check. If you can't balance it, it's the wrong answer. And that's good for every equation. If you can't balance it, something's written wrong, a formula's written wrong, or something you've predicted is wrong. Okay. Decomposition reactions. When things decompose, it's also redox. These are all different redoxes. What's going to be useful to you is knowing that polyatomics will decompose to gases. And by gases, I mean simple gases that you already know. And it'll leave behind something you already know. So don't be trying to create new and strange things, because you're not doing it right then. So let's start with magnesium carbonate. Magnesium carbonate is heated. Heated is different than burning. Heated means you put it on a hot plate. So you just have an arrow. If you want to be fancy, that means heat, but you don't have to. All right. When things with polyatomics decompose, all you're going to do is kick off a very, 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 very common substance, a common gas. This will decompose to a common gas and leave behind something you kind of already know. So what do you think what kind of gas, just in your gut, do you think comes off of? It's CO2. And what does that leave behind? MgO. Now, a lot of students are like, how do you know just oxygen didn't come off? Well, if oxygen came off, you'd be left with like MgC or maybe a CO. It's like something it doesn't make sense. Okay? And you could try to take off O2 and do MgCO2, but it's something you wouldn't know. Again, it's going to be something that's common. And I don't know if y'all remember ever doing it. I know y'all burnt magnesium, and you take the magnesium strip and you put it in the flame. What did it look like when it was done? White powder. That white powder was magnesium oxide. So these are salt crystals, shiny crystals, and after you put it on a thing, you get the white powder, and carbon dioxide had left. So is this balanced? Yeah, it's balanced. Okay, potassium chlorate is heated. Now, this term in the presence of implies a catalyst. What's a catalyst? Speeds up the reaction, but isn't part of the reaction. So you don't have to write it down at all, but if you have to write it down, you can put it on the arrow, but it's not required. I mean, they might say in the presence of, and you know it's a catalyst, but you're not going to have to ever indicate it. Now, polyatomics, when they decompose to gases. So think about what gas could come off of this and leave behind something you know. That chlorine with those weird oxidation states isn't going to come off. So what do you think? O2 leaving behind KCl. Okay. So to balance this, I just see I have 3 and 2. So I'm going to put a 3 here and a 2 there to get my oxygens the same, making me need a 2 there. How do I know that? Those chlorates are going to just make chlorides. Bromates, bromides, fluorates, fluorides. Yeah? You can try it and it won't balance. The question was, how do I know it doesn't make potassium hypochlorite? You can try. Spend about 2 minutes trying to balance it. If you can't, you're going to have to try something else. And I know from experience it doesn't, because hypochlorite is very unstable, so it's not going to do it. All right, so this last one, whoa, this one's fun. And I want you to try to tell me how to do it. Ammonium carbonate. This is fun. How many polyatomics are in there? 2. So we're going to have a whole bunch of stuff coming off of here. Let's take it one polyatomic at a time. What do you think is going to come off of ammonium? What? How about ammonia? Ammonia is a very, 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 very gaseous-y gas. When y'all go to the store and buy ammonia, you're not buying ammonia. Ammonia is a gas. You're buying ammonia in water. So you're actually buying, and it's not balanced, but this is what you're buying. The second you open it up, ammonia is what you smell. That's what's coming off as gas. Okay? So this thing, super, super, super easily decomposed. And that's what's happening there. It's going to kick off the ammonia. What do you think is going to come off of here? CO2. Now, I'd say go ahead, but there is something missing. We do have another product that comes off. it's water. If we were to do this and try to balance it, it wouldn't work, so something's up. And we do produce water as well. And that actually makes it balance, except we need 2 of these, 6, 7, 8, and now it balances. Okay? Y'all good in the hood? Okay. Let's try a combustion reaction. Now, in order to be successful in all your different kinds of combustion reactions, we often combust hydrocarbons. Up to this point, your teachers have lied to you. What have they said that combustion is? That your products are carbon dioxide and water, right? Okay, that's only the combustion of hydrocarbons. But technically, you can combust anything in the whole wide world. And all that happens is oxygen will smack onto each individual element in whatever you're combusting. And I'm going to show you that. But looking at here, I see an issue right away, methane. There are some expectations of organic compounds that you guys have to know for the AP. So I'm going to give you your mini list right now. This is nothing of what you need to know. You need to be able to write formulas for these. And I'm going to show you how easy it is, and it's not that hard. Okay? Those of you who are in pre-AP had an extensive organic nomenclature experience. Those of you who are in regular, I'm not showing you anything that's hard. So first off, you need to know your prefixes. These prefixes, 1 through 10, are good for alkanes, alkenes, cyclos, and alkynes, for all of them. 1 is meth, 2 is S, 3 is prop, 4 is bute, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. You have to know those. Okay? Alkanes are all single bonds. So if I ask you the formula for pentane, how many carbons is that? C5. And rather than memorizing this formula, I don't want you to. We don't do this enough right now until you get to organic for you to really memorize it. Frickin' if you need to, draw out 5 carbons or put them in your head. How many bonds does each carbon make? 4. So we're going to fill missing bonds with hydrogens. That's what alkanes are. Carbons and hydrogens all singly bound. So we're going to have 5 up top, 5 below, and how many more? 2. So it's 5, 10, 12. So it's C5H12. With this information, you can name any alkane between 1 carbon and 10 carbons. Okay? Cyclos you treat exactly the same way, except we put them in a circle. So what would be the formula for cyclobutane? 4 carbons, so we'd have carbon, 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 carbon. Right? Now I have to fill them to have 4 bonds with hydrogen. So how many hydrogens go on this carbon here left? 2. How many here? 2, 2, and 2. So it's C4H8, right? Okay. Alkenes are indicated by having, and we're only doing simple alkenes, and the only simple alkenes will show up on the AP, if they show up at all, and alkynes, double bond and triple bond. There's different types of alkenes. Let's say if I say propene, okay? How many carbons is that? 3 carbons. Since I'm saying propene, one of the bonds is a double bond. Only one for now, until next year. So now I have to fill in the H's. How many H's go on this first C? 2. How many on this next C? Just 1. And how many here? 3. So 1, 2, 3, 4, 5, 6. So what's my formula? C3H6. Okay? And then if I were to do an alkyne, same business. Let's say I say butane. 1, 2, 3, 4. I don't care where I put the triple bond. I'm not naming it. I just want a formula. So I can put the triple bond here or here or here. It doesn't matter. So these are single then. So how many H's on the first C? 3. How many on the middle C? None. How many on this C? None. And 3. So it's C4H6. So that's how you find formulas for all these different things you need in reaction writing. I think it's the expectation is pretty simple. okay? And you're not going to see a ton of them. I just want you to know how to in case they show up. So now let's go back and answer our methane burned in the presence of oxygen. What's the formula for methane? CH4. Burned in the presence of oxygen. That is combustion. And again, I don't like the word. I don't want you to think oxygen's catalyst, so I'm going to say burned in oxygen. So what your teachers lied about is you really didn't think about it. You were just like, oh, CO2 and H2O. Why is that? This oxygen smacks into all the elements present. So that's where we get the CO2 and the H2O. So we have 1C, 1C. I always do O's last. 4 H's, and I need 4 O's now, so I'm going to put a 2 there. Do O's last. If you get that weird O where you have a odd number of O's, say you had 7 O's on the right, you could do 7 halves O2 and then multiply everything by 2. That's a quick way to get it balanced. Lithium metal is burned in air. So I write lithium plus O2. This is combustion as well. So how does that work? Smack. What do we make? Li2O. Now how are these redox? Lithium went from a 0 to a +1. Oxygen went from a 0 to a -2. So in all these situations, something's going up and something's going down in charge. Up there, carbon went from a -4 to a +4. Oxygen went from a 0 to a -2. So we need to balance this puppy. See, I need 2 O's, so I need a 2 there, making me need 4 lithiums. Okay, zinc sulfide, what's the formula? ZNS is heated in excess oxygen. It's combustion. Anytime you see added to oxygen, smack, smack, what do you think we make? ZNO plus. Now, I'm just as a rule for practice, always go to your O2s. If an O2 works, it's the right answer, meaning if when you do an O2, CO2, SO2, NO2, if you get the correct charge change, it is the answer. So let's check. Zinc went from a +2. Oh, no, it's not zinc, sorry. Oxygen went from a 0 to a -2 in both cases, so that went down. Zinc has to go up. S, -2. Does zinc go up? Not zinc. Why do I say zinc? Sulfur. Sulfur is a -2, not zinc. Sulfur is a -2. It went up to a +4. So because that worked, the O2 would be the correct answer. We went in the right direction. Okay, is this balanced? No. So what do I have to do to balance this? Okay, I'm seeing 3 here, so I'm going to put a 3 there. That gives me 6 oxygens. So if I put a 2 there, that's 4, 5, 6. That makes me need 2 of these. Okay. The last one is going to cause a little bit of a problem. And I want to see who recognizes the problem. A piece of solid bismuth is heated strongly. What, Grant? Bismuth has 2 charges. How do I know which one to go to? There was a saying that you were taught in pre-AP. I believe in regular you guys got a list that you just got to look at. Who remembers this? Huge cups cracked. Good. As stand fell, huge cups cracked. What this is a list of ions whose largest charge is common. In other words, if the ion in question is in this list, the larger charge is the one that's most common. It's the one that's going to exist. Every other ion out there, they all go to the lower charge. So what are these elements? What is this one? Arsenic? No. Does strontium have multiple charges? Tin, right? iron, mercury, copper. And you didn't learn chromium as having multiple. Chromium actually has more than 2, but its 2 most common are 2 and 3. So this is chromium. All right. So is bismuth in that list? No. Since bismuth is not in the list, the lower charge is common. So that's the one we're going to go to. So when in doubt as to what charge you're going to make, you're going to use as Stan fell, huge cups cracked. So bismuth has 2 options. What are bismuth's 2 possible charges? 3 and 5. So we're going to go to 3, making the formula so I see a 3 and a 2 here again for oxygen, so I need that common factor. So I get my 6, and that means I need a 4 there. This is not going to be heavy on the test. This whole thing is for me to introduce you to a quick way to do reactions, especially under the pressure of the AP. I will revisit this spontaneously in the version of maybe little quizzes here or there. Do your homework. Kind of put it in your back pocket and have it on the ready, because it is sure a lot easier to write formulas like this and have to do it the long way. Okay, so you have time to work on your homework. Omit number 11 from homework 2F, and then don't forget tomorrow, surprise activity. So bring your lab books and a graphing calculator if you have one. If you don't have one, I hope you know how to graph with it and you can borrow one of mine. Hold on one second.